So let's start our morning section. So we are very happy to have three distinguished lectures for this morning. The first talk were given by Professor Birkar. Professor Birkar is a distinguished professor of Yale's Mathematical Sciences Center at Tsinghua University. He is a member of Academia European and the fellow of the Royal Society. He received the first medal in 2018. So he will give a talk on the rich world of the Fano geometry. So let's welcome.
Okay, thank you for the kind introduction, and also for thanks to ICBS for the invitation to give this talk. So I'm going to talk about, as you see the title, the rich world of Fano geometry. Fano varieties and many things associated to them, they are central in modern mathematics and even before that in a historical sense. So let me just get a couple of things fixed. First, I will work for simplicity over the complex numbers, although this is not really necessary. Many things make sense over other fields, but for now, that doesn't matter too much. And remember, at least for the students, that algebraic geometry is basically about studying or classification of quasi-projective varieties. These are subsets defined by polynomial equations in the projective spaces. So that also includes all the affine ones. Of course, we have schemes and so on, stacks and more general stuff. But the reality is the varieties are the most important. Other things are mostly for technical reasons. Now, among these spaces, Fano varieties, they form a very important class. They play a very fundamental role in geometry, not only in algebraic geometry, but overall in geometry and well beyond. They are especially important in birational geometry, as you will see later on. I will talk more detail. But they are also very interesting and very important from a computational or constructive point of view of mathematics, because they happen to be a class of objects which are much more suitable for computations. Other classes are much harder to do computations with, but Fano varieties are actually much more suitable. They are also closely related to many other areas of mathematics that includes algebra, for example, in different ways. I will give you some examples in the lecture. And of course, also related to, in a very central way, fundamental way, to arithmetic geometry, to number theory, because again, they happen to be one of those spaces which are maybe more approachable from the arithmetic point of view. But they also play a very important role in mirror symmetry and more generally connections with mathematical physics. Again, I will talk about this a bit more detail. They also are central in differential geometry, which I forgot to list here, but also in applied algebraic geometry. They actually happen to be mostly the kind of spaces that appear when you talk about applications to real-world problem. Here, I don't mean like string theory and so on, but I mean just down-to-earth world, real-world kind of problem. Mostly, they happen to be Fano varieties or something related to Fano varieties. In particular, toric, which we will see later. The toric are basically also Fano. Okay, so let me just remind you or the younger generation here what Fano varieties are. A Fano variety is basically a projective variety X, can be smooth, or also we allow a mild form of singularities. For now, I will just say mild singularity. Later on, I will give you some definitions, where the key property is that the anti-canonical divisor or bundle is positive or ample. Remember that the canonical bundle is defined by the top degree differential forms. So this is related to differential forms, and of course, not surprisingly, also related to differential geometry. And here I give you a list of very basic examples of Fano varieties. The most familiar one is the projective space. This is, in some sense, the simplest space in algebraic geometry, although it's actually not so simple, but at least one of the first spaces that we see, and it happened to be a Fano variety. Also, if you take hypersurfaces in Pn of low degree up to n, then they are all Fano varieties if they have reasonable singularities. And if you go back to the ancient world, where Greek mathematicians, they studied conic sections, and they all happen to be Fano varieties. They basically degree 2, defined by degree 2 equations, so they happen to be Fano varieties. More generally, we can intersect hypersurfaces of the right degrees. So as long as the degrees are not too large, then what you get will be a Fano variety. Also, if you are familiar with the technology of toric geometry, then toric varieties are basically, they are not all Fano, but they are very close to be Fano. In fact, they are Fano in some sense, in a more general form, as we call them, Fano type or log Fano. So all toric varieties, at least the quasi-projective one, or more relevant here, the projective toric varieties, they are all basically Fano in some sense. And so that's one way it explains why they behave so well, because they happen to be Fano. And among these toric spaces, there are a special kind which are called weighted projective spaces. These are more general forms of usual projective spaces, and they are also very useful for computations and constructing examples and so on. Also, inside these weighted projective spaces, you can also take hypersurfaces and take intersections and so on. Again, that gives you a lot of examples. In fact, the vast majority of examples of Fano varieties, Calabi-Yaos, and so on, they are constructed using this toric technology. And finally, Grassmannians, they also happen to be Fano varieties. So here you have a whole list that you can keep in mind when I talk about Fano varieties. Now, Fano varieties are not important only in modern mathematics, but in fact they have been really central in the history of mathematics. Well, first of all, if you go back to the ancient times, then they basically were studying degree 1 and degree 2 spaces, which happen to be Fano varieties. So in some sense, you could say the Greeks, at least the kind of geometry that was related to equations, were basically about Fano varieties. But if we forget about the ancient times and go to the 19th century, that's where the real fun starts, then we have the Italian school of algebraic geometry, which basically developed algebraic geometry in dimension 2. Of course, we also have algebraic geometry in dimension 1, but when we talk about Fano varieties in dimension 1, you have only one space, which is just a projective line. So in that sense, dimension 1 is not very exciting. Excitement starts in dimension 2, and that's essentially started in the mid-19th century by works of Cayley, who is not Italian, but most of the others were from the Italian algebraic geometry school, especially Cremona, Noether, Enrique, and so on. And later on, they also studied some three-dimensional spaces, which happen to be Fano varieties, but they did not develop enough, so it was taken over by other people. In fact, in the 1970s, algebraic geometers, especially in Russia and Japan, including Iskovsky, Manin, Shokuro, Mori, Mukai, and so on, they continued this work of the Italian school of algebraic geometry, and they made it more rigorous because the Italians apparently didn't do a complete job. They had ideas, but not a complete proof. But these guys later on, they developed this, they made it rigorous, and they expanded. And what they did in the 1970s and later in the 80s, they classified Fano varieties in dimension 3. And that was very important, not just for the geometry of Fanos, but also it led to the development of algebraic geometry in dimension 3, basically, or the classification of algebraic varieties, not only Fanos. So among all the algebraic varieties in each dimension, Fano varieties are a special minority, but they happen to be very powerful. So it's like if you look at each country, and of course it can be a big country, but sometimes a small minority, they are much richer than everyone else, much more powerful. So in some sense, Fano varieties are like that. So although they classified all kinds of algebraic varieties, but in fact, the Fanos were always there, even if they were talking about other spaces which were not Fano. In particular, these people, many of them from the Japanese and the Russian school of algebraic geometry, they realized, in particular Mori, who is sitting here, that you can run a program similar to what the Italian school did, but in dimension 3, where in this program, which is called the minimal model program, every step is about fun in some general sense that I will explain later. So globally, maybe you are not talking about a Fano variety, but in some local or relative sense, every step of this program is about Fano. So that's why this world of Fano, when you look at it in this more general sense, is such a rich world because it's relevant to all algebraic geometry, not just the classical Fano varieties. And later on in the 21st century, especially around the 2000s and after that, then also algebraic geometry in higher dimension was more developed. So by now, we know a lot of things in every dimension, although this is not a complete program, but we know a lot. And again, Fano varieties happen to be one of the key ingredients of this whole subject. But on the other hand, connections with other areas also has flowered in the last few decades. For example, there are strong connections with the homological algebra world. For example, derived categories. In the derived category of algebraic varieties also, you can see basically the role of these Fano varieties or Fano geometry. In the birational geometry world, we have the minimal model program, and then there is a parallel process in the derived category world, where again, you have a step-by-step program, and then these steps basically are about Fanos. In a quite different direction, there is also a strong connection originating in differential geometry. This is about Kähler-Einstein metrics and is translation or equivalent conditions in algebraic geometry, which is called a K-stability. So there is a huge number of people involved in this whole thing, and this is essentially just a sample. Of course, it's not the whole, it's not an extensive survey of Fano varieties, but I think this already makes it clear. So if you look at the history of mathematics, then you see that at least at several points, big advances have been related to Fano varieties. Okay, so what is so special about Fano varieties? Why we should focus on this class where the anti-canonical bundle is positive? Why not on the class where the canonical bundle is positive? Well, that's because Fano varieties enjoy some really special properties. First of all, they are the most familiar varieties when you start to learn algebraic geometry. The very first examples that you see usually happen to be Fano varieties. And that's not surprising because when you look at low degree equations, they usually give you Fano varieties. And of course, in a first course on algebraic geometry, the first examples are degree 1 and 2 and 3 and so on. You don't jump to degree 1000. So naturally, you get Fano varieties. But another reason is more intrinsic, and it's because they have such a rich and beautiful structures on these spaces. Other kind of spaces, for example, where the canonical bundle is positive, or those are called general type, of course, they are interesting, but in some sense, they are much more boring compared to Fano varieties. They don't have the same kind of rich geometry. One of these properties or structures that Fano varieties enjoy is symmetry. In the case of spaces of general type, or spaces which are negatively curved in terms of differential geometry, they don't have too many symmetries. Their symmetries happen to be finite, basically. But in the case of Fanos, symmetries can be much larger. For example, if you just look at the projective space and look at the automorphism group, so that already gives you matrices, basically, which of course is interesting, but it gets much more interesting if you look at birational automorphism group or bimeromorphic. That's a much larger space, and it gives you an algebraic object, a group, which is very complicated, and it has a very interesting connection with the geometry of these spaces and many other spaces related to them. Another thing which I mentioned earlier is that Fano varieties are much easier to do computation with. So that's one reason we work with them, because, as I said, examples many times happen to be Fano varieties. And another reason is that Fano varieties are much more likely to be classified than other spaces. And so that's what makes it more interesting, because you always feel that I can do this, I can classify these spaces and so on. Although in practice it's not so simple. This is actually very, very complicated and challenging, but still that's what makes it very interesting. It is help that you can actually classify them. And as I mentioned before, they are much more relevant to the real world, in particular through toric geometry. And another reason is degeneration. Quite often, other spaces like Calabi-Yau's or general type varieties, they can be degenerated. You can take a limit or somehow approximate, degenerate these spaces into Fano varieties or union of Fano varieties or something related to Fano varieties. So, for example, in the mirror symmetry world, this is probably one of the most common techniques. To do something about Calabi-Yau's, you degenerate them into a union of Fano varieties, and then you do computations. So, in fact, this is one of the main ways even to construct mirrors and so on. Okay, so again, that's just a sample of why Fano varieties are important. Now, I don't want to just stay with Fano varieties. The story becomes much more interesting when you expand this notion into a relative version. And for this reason, I define Fano fibrations. A Fano fibration is basically a morphism. Here I write a contraction, but I think you can ignore this. It's just a technical term. It basically means this is a projective morphism, and you want with connected fibers. Connected fiber is not a big deal because you can always achieve this. So you can just think about a projective morphism. Again, you want singularities to be mild. And the anti-canonical divisor we want to be this to be positive relatively over the base, not globally. These varieties may not be projective. Only the morphism is projective. So this positivity is a relative notion here. Maybe, at least for the student, you can think of this as a vibration where all the fibers are fun, roughly speaking. Here I give you, again, a list of elementary and non-elementary examples. If you take any global Fano variety and take Z to be a point, then you have one of these Fano vibrations. So this includes all the usual Fano varieties. But also take any Pn bundle over an algebraic variety Z. Then this is automatically a Fano vibration. In particular, this includes all the vector bundles over the Z, because for any vector bundle Z, you can take the projective bundle over the base. So you can view all the vector bundles on algebraic variety as Fano vibrations. And in fact, we use, for example, in some recent work, we use these things to construct moduli spaces of vector bundles with some stability conditions and so on, and we use this kind of structure. So this immediately connects this story with the story of vector bundles, for example, which may not be at all obvious that this is related to Fanos. And another object, these are called Mori fiber spaces, and I will not define this, but this is, again, a kind of Fano vibration, very central in birational geometry. For example, like a conic bundle. But also there are other ones which may not be obvious that you can call them Fano variety, Fano vibration. These are, for example, flipping contractions. Again, these come in the birational geometry world, or divisorial contractions. We can view these things also as Fano. And finally, if you just have the identity map from X to Z, X to X itself. So what that means? That means you just have one algebraic variety. There is really no vibration. You just have the identity. We can still think about this as Fano. And this makes it very interesting, because this means that singularity theory is just a subset of this world of Fanos. At least the kind of singularity that we are interested in. Because, according to this definition, this is actually a Fano vibration. And in fact, many of the statements that we prove in the birational geometry world is in this setting. Not just the global setting, but in this setting. So that also tells something about singularities. So that's why this becomes such an interesting story. So with this setting, then the question is, well, how can you study the geometry of a Fano vibration, X to Z? How can you relate the geometry of X, of the base, of the fibers, and so on? So there is a huge number of questions and results in this setting. Let me go back to the birational geometry setting and look at the minimal model program. Suppose that I start with an algebraic variety W. For simplicity, let's say this is smooth, projective. Then the minimal model program is basically a step-by-step program which transforms our space W birationally until at the end it gives you a space which is in some sense it has a richer geometry, or it has a more special geometry than the original one. So in the case of surfaces in dimension 2, these steps just contract curves every time, which are called -1 curves. But in dimension 3 and higher, this is much more complicated, because there are different type of steps that you can get. For example, you have divisorial contractions where a divisor may be contracted, or you can have flips where something is contracted but no divisor and these are much harder to work with. And also you can get, in the end, you can get this Fano vibration. This is one of the main outcomes. So assuming that this program, everything works, in the end, you get a space, and this space will have the following form as in the conjecture here I state at the end. Either this space at the end admits a Fano vibration, or a Calabi-Yau vibration, or it becomes completely positive. So this makes it clear why Fano vibrations are important in birational geometry. Because the outcome, not always, but many times, happen to be a Fano vibration. But more importantly is that every step in the program is about Fano. A divisorial contraction is a Fano vibration. A flipping contraction is a Fano vibration. So every step is related to this Fano geometry. So I think this makes it very clear why Fanos are important in birational geometry and more generally algebraic geometry. So one of the steps that I mentioned are flips. A flip, or a flipping contraction, is a birational Fano vibration, which is non-trivial. That means that something is being contracted, but it does not contract any divisor. So for example, you can have a threefold, and one single curve is being contracted, but no surface is contracted. These are flipping contractions. And they are necessary in order to run the minimal model program. But you have to show that when you have these flipping contractions, you can perform an operation. So this is only part of the flip. In order to complete the flip, flips have two sides. You have a negative side and then a positive side. You have to construct the positive side as well. And this construction can be translated into this algebraic statement, which might be more understandable to those not familiar with the story. So what you need to do is you form a graded algebra of sheaves, taking all powers of the canonical bundle, and then you need to show that this is a finitely generated algebra. So it becomes an algebraic statement. Okay, so I'm not going to explain how this is proved, but just proving that you can complete this flip process, it happened to be one of the most complicated ingredients of the story. And in dimension 3, Mori first proved this for terminal singularities, and later on, Sokurov extended that to more general singularities and also extended to dimension 4. And based on these works, then other people, Heiken, McKernan, myself, Cassini, and then we show these flips in every dimension. So that gives us one of the main ingredients of the minimal model program. But anyway, my point was that this is also basically about Fano. In fact, the flip is very interesting because, as I said, it has two sides, a negative side and a positive side. The negative side is a Fano. The positive side is a general type. So this is one place where negative geometry and positive geometry, they come together. Okay, so I mentioned singularities many times without giving you any definition. So for completeness, let me just give you the definition. So there are different ways to study singularities in geometry. So, for example, if you go back a long time ago, deformations people used to study singularities. But in birational geometry, we need something more precise, and we measure singularities using resolutions of singularities. So that means that if you have an algebraic variety, or more generally, if you have a pair where you have a space X together with a boundary divisor B, this b is a divisor and its coefficients are between 0 and 1. If you have never seen these things, maybe you can just ignore, although later on in the talk I will still need this notion of pairs. But for now, you could just think about one single algebraic variety. Okay, and then what you do to measure the singularities, you first do a resolution of the singularities. We know this exists by work of Hironaka. This process, although we know it exists, it can be very complicated. Once you do the resolution, then you pull back the canonical divisor or together with the boundary divisor, and then you can write it down. So let's say the resolution is W2x. I can write this down as KW plus a correction term, BW. And then the singularities are defined by looking at the coefficients of this BW. The larger the coefficients, the worse or the deeper the singularities. But for our talk, one type of singularities, maybe most relevant, these are called epsilon low canonical. It just means that the coefficients of BW are not bigger than 1 minus epsilon, where epsilon is some number. And if I take epsilon to be 0, then traditionally these are just called low canonical. And if I don't focus on the epsilon, just know that I have some positive epsilon, these are called KLT or Kawamata log terminal. So maybe just keep in mind epsilon LC. Or better, maybe just think of this as a way of measuring singularities using resolutions. And then here I list some elementary examples of singularities. For example, let me just jump to the last two. If you take a cone over an elliptic curve, then you get a 0 low canonical singularity. And if you take a cone over a rational curve of degree n, then you get a 2 over n low canonical singularity. So the larger the n, the more complicated the singularity becomes. Okay. So now in the world of Fanos or Fano fibrations, what can you do? How can you study a Fano fibration? Well, for a Fano, in general, in algebraic geometry, to study an algebraic variety, if you want to understand it fully, what you need to do is to take a positive divisor on it. In the differential geometry world, maybe you talk about scalar forms and so on, or some positive metric. In algebraic geometry, we usually take ample divisors, or even better, very ample divisors. If you identify an ample or very ample divisor and use that to embed it into a projective space, then at least theoretically you fully understand your algebraic variety, because it totally determines the variety. Now, in the case of Fanos, minus k is already ample by definition. So there is no reason to look for any other ample. This is what you should be working with. In the general type case, k is ample. So you should work with k. In the Fano case, the most natural thing to do is to work with minus k. But minus k, although it is ample, it is not, in most cases, it's not very ample. So it doesn't fully give you the geometry. In order to understand your variety, you have to take all the multiples. Or you have to take multiples large enough to capture the geometry. Minus k alone is not enough. You need to take minus 2k, minus 3k, maybe minus 1000k. It depends on your situation. So complement theory is basically this machinery, this technology. You look at this minus nk and try to understand them as much as you can. And this was introduced in a systematic way by Shakurov. So he said, well, look at this minus nk for different n, and we study this relatively over the base. We can fix a point on the base and see what we can get. So a complement basically is the choice of one of these n's and the choice of an element in minus k when you look at it as a linear system. And I write this down as just a delta. So delta n times delta comes from minus nk. But I can also formulate it in this way. So an n complement then is of the form k plus delta, such that x delta must have good singularities. We don't want a completely random guy. Secondly, it must come from this minus nk, and that just means n times k plus delta should be linearly trivial. That just means n delta is in minus nk. So that means that I am looking at minus nk system. And the question is how large you should take n in order to get something non-trivial about this situation. You don't want to take n to be too large and too arbitrary, because even if you, let's say, work in dimension 2, you want to take n so that minus nk becomes very ample, then the n can be totally arbitrary. It can be millions, billions, there is no bound. Then that's not very interesting. It's more interesting if you can take some relatively small n, but still capture the essence of the geometry. So this is what complement theory is about. For example, in dimension 2, let's just look at the purely local case, where we take just a germ of a singularity. So x to z is just identity. And suppose this is one of those KLT singularities, then there is a classification of this type of singularities. There are A-type, D-type, and E-type. A-type corresponds precisely to when you have a one complement. So these complements can detect the type of the singularity. And type D are those for which you have a two complement, but not a one complement. And E-type are those you don't have 1 and 2, but you have 3, 4, or 6. So you just have 1, 2, 3, 4, and 6. You have only these few numbers to basically capture the essence of these singularities. You don't need 10 billion. You just need up to 6. So this is the main point. In dimension 3, another example is if you take a smooth Fano threefold, then you always have a one complement. In fact, inside of this minus k system, you can find a smooth element, which is a k3 surface, and that gives you a one complement. This complement story also plays a key role in the proofs of existence of flips, which I discussed before, in dimension 3. So that was one of the key ingredients of, for example, Mori's proof, and later on Shakurov's proof. Basically, you take a complement in order to construct the flip. So then finally, perhaps the most general statement in this direction is that in every dimension, there exists one n. We don't know exactly what that n is, except in lower dimension, such that no matter what Fano vibration you have, you always have an n complement. So the n will be depending only on the dimension. It does not depend on your Fano vibration. Okay, so there are many, many questions that you can ask in the setting of a Fano vibration. And one of those, which is very natural from the point of view of birational geometry and singularity theory, is related to singularities. So suppose I have a Fano vibration, x to z. Well, how do singularities behave? Can you relate singularities on x and z and on the fibers, for example? You can ask this question, of course, more generally, not just for Fano vibration. And indeed, even when you are interested in the Fano case, proofs often involve other kind of spaces which are not Fano. It can be, for example, general time. So this is a fundamental question in algebraic geometry, as well as in, for example, arithmetic geometry. you look at elliptic curves and then take models of elliptic curves, then the singularities of the special fibers are very important to understand the number theory of an elliptic curve defined over a number field. Okay, so one of the examples, just to give you a taste of what I mean here, is if you take a threefold fibered over a surface which is a conic bundle, so roughly speaking that means that the fibers are mostly just the projective lines, but you can have special fibers which are more complicated. If X has so-called terminal singularities, then the base Z will have canonical singularities. So I did not define this type of singularities, but as such they are defined in the same way that I defined epsilon LC singularities. But in a much more general form and in every dimension, the next theorem says that if the total space X has epsilon LC, then the base will always have some delta LC, where delta will depend only on epsilon and the relative dimension. So the previous example is just one example of this more general statement. So unfortunately, this is a very long story. There's no time to go into this any deeper. But there are also still very hard questions remaining in this direction. For example, if you take a Fano vibration X to Z, then I already explained the notion of a complement. So I told you that in the setting of Fano vibrations, complement always exists for some bounded number n. But now, if we insist on the singularity of the complement to be nicer, for example, to be KLT, then this is not proved. In fact, even in dimension 3, this is still a very hard problem, and we know very little about this, except in very special cases like toric case. Otherwise, it's an extremely difficult problem. Another problem related to this setting, again, is when you take a Fano vibration, and if you take the total space to be nice, like epsilon LC, then it's conjectured that on the base, you can always find a Cartier divisor. Cartier is the key point. Cartier divisor, which is effective, and so that if you pull it back, the singularities still are not too bad. So maybe if we specialize to one particular case when the base Z is just a curve, so think about a Fano vibration over a curve, then this is basically saying, if you look at the fibers, all the fibers, general and also special fibers, they cannot be too singular. There must be a universal control over the singularities of the fiber. And again, this is still a very hard question, even in dimension 3. But this type of problems is what makes this subject very interesting, because it somehow, did they make sense even in a purely local singularity case when there is no Fano? You don't see any Fano. You just have a germ of a singularity. These two conjectures still make sense. But in order to solve this kind of problem, you are somehow forced to go into the world of Fanos. So I don't have too much more time left, so let me maybe be a little bit more quick. So as I mentioned before, Fanos are also closely related to algebras, and here is one way. It is not the only way. Suppose I look at an algebraic variety, but in our case, right now, it's just a projective space, and I take all the birational automorphisms of this space. In the case of projective space, this is called a Cremona group, Cn. And in fact, the study of this group for P2 in dimension 2 was one of the main starting points of the algebraic geometry school of the Italian. Cremona, who started studying this problem, him and people around him and his students, I guess, this is what led to this Italian school of geometry, basically. Okay, so we can define this group also purely algebraically, even not talking about any geometry. It's just the set of all the automorphisms of a polynomial is a field given by n variables. You look at all the automorphisms of this field over the ground field, which is K. So to define it, you don't even need geometry. But in order to answer questions about these groups, usually you need some geometry. So one of the things that was proved only in the last 10 years or so is that these kind of groups satisfy very nice properties. One of these properties is called the Jordan property. The Jordan property means that if you look at all the finite subgroups, they of course may not be abelian, but the Jordan property says that they cannot be too far from abelian. So if you take any finite subgroup, you can always find an abelian normal subgroup so that the index is universally bounded, not depending on this finite subgroup G. So this is called the Jordan property. And it was proved only in 2016. And another fact about these groups, again, quite hard to prove, is that they are not simple. So that means that they have non-trivial normal subgroups. And this was proved by Blank, Lamy, and Zimmerman. But these statements are not proved purely algebraically. They are proved using algebraic geometry. You relate the problem to a problem about, basically about Fano vibrations. For example, in the case of the first statement, if you take a finite subgroup, so this is a subset of birational automorphisms. Well, first you need to find another space birationally where this group is actually acting regularly, not just birationally. And then you run a minimal model program respecting this group, and it ends with a Fano vibration. That Fano vibration is then key to proving this statement. Okay, another direction, which is related more to computations, is about computational, explicit, or effective, or constructive, whatever you call it, algebraic geometry. That means listing examples, making things more explicit. That means that doing computations, if you can, using computers or by hand and so on. And this makes much more sense in the case of Fanos compared to other spaces. For example, even Calabi-Yau is very hard to do computation. In fact, most of the computations I have seen related to Calabi-Yau, they also somehow involve Fano varieties. Like you take a Fano first, then you construct Calabi-Yau using the Fano. In fact, basically using complements on Fano varieties. So a very simple, not maybe so simple, but at least easy to state, is that if you look at all the Fano surfaces, then they basically, except P1 times P1, they all come from P2 by just blowing up a few points. So this is a very concrete, explicit way of talking about these spaces. So this is what I mean by explicit and effective. In dimension 3 also, there is a whole classification of all the smooth Fano varieties by Iskowski, Mori, and Mukai. But when you go to the singular one, then we know many things, but still a lot of things are missing. So even in the three-dimensional case, there is still a huge number of things to do to make things more explicit and effective. In fact, we have many abstract statements in dimension 3 and every dimension, but they are very far from being effective. So just as an example, if you look at all the Fano varieties of a fixed dimension and with one type of singularity, then we know that they form a bounded family. But we have no idea how large this family is. It's still very non-effective. Even in dimension 3, we don't know. If you want really to have a much deeper understanding, you need to make things more explicit, more effective. Effective would be like saying, well, all these varieties can be embedded into, I don't know, P20 with equations of degree at most 50. If you prove something like that, then that is a much more effective, stronger statement than just proving something abstract. So there is a huge number of problems in this direction, but I think that is just enough. And then there are connections with mathematical physics in different directions. One of these directions is related to mirror symmetry. So one of the first maybe general results or constructions in the direction goes back to Battier. So he wanted to construct mirror Calabi-Yau's in a systematic way. And then he said, well, you first start with basically a Fano, toric Fano variety, a nice one. That is given by some fan or by some polytope. And then if your polytope is nice enough, you can look at the dual of this polytope, and then you get another toric Fano variety. So you have now two Fano, both of them are toric, so very combinatorial. Then inside each of these Fanos, you look at minus k. This minus k is a linear system, and then you can look at this linear system. You could take the whole family or just take some members, although it makes more sense to take the whole system. So you get a whole bunch of Calabi-Yau's, because inside Fanos, when you take minus k, it gives you automatically Calabi-Yau's. And then now you have two Calabi-Yau's, or you have two families of Calabi-Yau's. And then he said that, well, these two are mirror to each other. So this was one of the main ways to construct mirror Calabi-Yau's. But as you see, this involves Fano varieties. Now, in the setting of Fanos, purely Fanos, also there is a mirror symmetry conjecture due to many people, which says that if you have a smooth Fano variety, then there is a mirror. But the mirror is not necessarily a Fano variety. It's a so-called Landau-Ginzburg model, which in many cases is like a torus, and then together with a function on this torus or this space, and then this conjecture says that, well, the geometry of the Fano X is somehow reflected in the properties of this fibration, basically. That function gives you a fibration. So a lot of things have been done in this direction, but of course it's very far from being complete. In a very different direction, there is another way of connecting Fanos with physics. And that is in the setting of F theory. In F theory, you quite often consider Calabi-Yau's which have an elliptic fiber structure. For example, you have a Calabi-Yau threefold, which is fibered over a surface. The fibers are mostly elliptic curves. Of course, you have special fibers as well. And then to understand this Calabi-Yau, naturally what you need is, one of the first steps is to understand the base. You can also have that in higher dimension. You can have a four-dimensional Calabi-Yau fibered over a threefold. These two cases are especially more relevant to physics. And then in this setting, you want to control the geometry, which also then can tell you something about physics. So for example, one of the very basic things to try to do is to say, well, on the base, for example, the Picard number is bounded. Because we already knew this from general results in algebraic geometry, but talking to physicists, my collaborator, Sanju Lee, who is here, he told me that physicists don't really care about this kind of statement. You have some abstract boundedness. They want something concrete, which also kind of supports more the previous discussion about explicit and effective algebraic geometry. They want something explicit. They want to say, well, the Birkar number is at most 1,000, not just there exists a bound. Because what you can do with there exists a bound in physics. You want some particular number. And then we worked on this problem, and then we finally showed that in this case, in fact, the Birkar number cannot be too large. At most 568. So if you think about the whole universe, 500 is not such a big number. But more importantly, this is proved purely using geometry. There is almost no input from physics, except the original setup where you have an elliptic vibration. Beyond that, we don't use anything from physics. So this is purely algebraic geometry. But what is the nice thing about this is, of course, I thought about this type of problem for a very long time because it already appears in my work. For example, in the proof of boundedness of Fano varieties, these kind of statements actually appear in some form. So it was very interesting to see that the process of proving this, it actually has physical interpretations. Each step tells you something about physics. So I was kind of surprised that something that I was doing for a long time actually means something in the universe. But I always thought that anything I do has nothing to do with reality. But apparently, there is some connection. So this is only the starting point. Now, if you do the same thing where the base is three-dimensional, for example. Well, let me go back to the two-dimensional case. A group of other people proved something even stronger, but not using just mathematics. They use physical arguments, so it's different from ours. But it looked like, talking to my colleagues, that when you go to dimension 3, the physics cannot really tell you almost anything. You cannot prove these kind of statements using physical arguments. But using birational geometry, we can prove similar things in higher dimension. Maybe not as nice as 500, with maybe 5 million. Or maybe more, but at least we can prove something, which for the moment seems that is way beyond the reach of physicists. So there is a lot to do here. I feel that birational geometry can contribute a lot to physics, and it has not been explored enough. There is a lot of more work to do. Okay, I have a couple of more slides, but I think not enough time, so I will just maybe stop here.
Okay, questions? Professor, so you mentioned the epsilon LC singularities, but could you please explain? So what can I read from this epsilon, dominant epsilon? For example, for more information of that, rather than just the abstractly for epsilon to delta epsilon. For example, can I read some topological information from the epsilon itself?
For arbitrary setting or which statement?
Maybe general statement. I'm not sure, just the kind of idea.
Well, it's not very easy to derive. So, for example, in the cone singularity example that I told you, you take a cone over a rational curve of degree n. And I told you that this has 2 over n singularities. 2 over n. So now if you fix the n, that means that this really tells you something about the singularity, and it makes it much more restricted. Fixing the n. So fixing epsilon basically means fixing this n. That means that fixing the degree or bounding the degree of the rational curve. But if you take more general epsilon LC. Of course, in some way this is special, but it's still very general. Epsilon LC is not so special. It's not so easy to derive like topological. So the topology, for example, the local fundamental group, we know it actually satisfies some very nice properties. For example, it satisfies the Jordan property, which I mentioned for the birational automorphism group. For local fundamental group, we have something similar. So there is some topological information, but this notion is still very, very general. You cannot just say, well, you have a finite list or this kind of thing. So I think maybe also good to say here that I think singularities are more interesting than global geometry because they contain global geometry as a very special subset. So anything you say about a projective variety or manifold, it already appears on some singularity. So singularity is a much more general notion than global geometry. But epsilon LC is nice, is not such a special thing.
Okay, thank you.
More questions?
So just ask a naive question. So in this conjecture, is a mirror Gibbs-Leno model is birational to the original Fano variety?
No, not necessarily. If the X may not be rational, for example, but the mirror, I guess, in many cases they are the toric, or for example, a torus. So I don't think they are mirror to each other, not birational.
Oh.
More questions? So I ask a quick question.
One at the end. Yes.
There is a yes. What is why 568?
Yeah. So in fact, the physics number is this Picard number -1, which is 567. So I thought there might be some. Maybe it's
why 567.
Maybe some kind of joke by whoever built the universe. 567.
So maybe I can ask you a quick question. So these Cremona groups for P2, they act on the moduli space or an open locus of the moduli space of n points on P2. Am I right? And then that thing actually has a braid group. So then there is a connection between Cremona group and the braid groups acting on point configurations on P2. Am I right?
Well, you have to be careful. The Cremona group does not quite act on points because they are birational. So
yeah,
it may not be defined at that point. If you take a finite subgroup, then that's a different story. You can say, well, it's acting on some open subset. But the whole group does not act because for any point you take, there will be some element of this Cremona group which is not defined there. So you cannot really act on it.
So then this connection between Cremona group or a finite subgroup acting on this locus, open locus, and the braid groups, is it existing in higher dimensions, beyond surfaces?
It should exist. I mean, if you, for example, it should exist. Why not? I don't see something special about dimension 2.
Okay. More questions? Okay, if not, let's thank Professor Birkar again.
穹苍广而恒千，物合多容。星云璀璨，黑洞冥冥。观测天象，探问宇宙，基础科学由此萌芽，照亮蒙昧世界。万物之理，数为基础，几何为根，方程为本。 数学家以思考重塑了人类对万物的认知，物理学家以智慧让我们掌握不可思议的能量。